Welcome to lecture 27 of Power System Protection course. So in the last lecture, that is lecture 26, we also discussed about the static comparators as relay. So in that we discussed regarding the duality between the static comparators. Like we have two types of static comparators available with us, that is amplitude comparator and phase comparator, and we saw the duality between these two comparators, how one of the comparator can be used to act or function as another comparator with the same input. So already we have seen this by adding different components of phase comparator and subtracting the phase comparator signals by providing it to the amplitude comparator. It will act exactly like the phase comparator. Similarly, the case for amplitude comparator, when it is implemented using a phase comparator, is same, and this is the concept of duality in between the phase comparator and the amplitude comparators. So also we discussed in that how we can implement various types of relays, like your overcurrent relay, directional overcurrent relay, then your different type of distance relays like your impedance relay, and also the reactance relay and move relay, how we can implement using different type of comparators. So we saw that overcurrent relay we can implement using the simple amplitude comparator and directional overcurrent relay we can implement it using the phase comparators. Similarly, your impedance relay can be implemented using the amplitude comparators, and your move relay and the reactance relay both can be implemented using the phase comparators. So already we discussed about these aspects, and today also we will talk more about the static comparators as a relay. In this lecture we will cover how the comparators can be implemented using the electronic circuits. Then we will see how a quadrilateral distance relay can be implemented using these static relays. So that is our objective here, and let us see. So so we will see here the development of an electronic circuit for implementing cosine type phase comparator. So here one may ask why we are not implementing the amplitude comparator, because implementing the amplitude comparators are simple, because we know we have the op-amp which acts as the comparator. In fact, it is the amplitude comparator. So there are many different type of ICs available in the market which directly can act as the amplitude comparator. So in fact, we need to design the phase comparator instead of amplitude comparator, because amplitude comparators are available ready-made, so not required to design for amplitude comparator. So let us see the development of an electronic circuit for implementing a cosine type phase comparator. Then we will see how we can implement a sine type phase comparator. So the concept here used is a coincidence waves method. So using the coincidence wave method, we can design this kind of comparators. Here you can see we have two signals. One is your SP and other one is your SM, which is one is a polarizing signal, other one is your measured signal. And if they are sinusoidal, both are sinusoidal, then it is very easy to find the coincidence period, right? So this is the phase angle, this is in the degree, right? So if we will see, to find the coincidence period for a 50 Hertz signal, what will be the time period? Time period will be 20 millisecond, and 1/2 of the signal will be 10 millisecond. So either we will see the positive coincidence period, right, positive coincidence period or negative coincidence period. So what is this positive coincidence period? Positive coincidence period is the period of coincidence and the same positive cycle when it is in the positive only in the positive cycle. Similarly, your negative coincidence period is the coincidence period, that is the coincidence period between the two waveforms in the negative half cycle, right. So here we are only will more concerned about the positive coincidence period, therefore we will talk about the positive coincidence period. So here if we will see SP and SM, if there is no phase difference between these two signals, then your coincidence period, positive coincidence period will be 10 millisecond, right. And if there is some phase difference, so then it will vary accordingly, right. So if you will see here in this waveform, here the SM is lagging SP by 90 degree, right. The phase difference between SM and SP is 90 degree lag, and which can be represented in the positive coincidence period as 5 millisecond, right. We can see here the positive positive cycle of these two waveforms are in fact coincidence for 5 millisecond, right. So therefore for 90 degree phase lag or lead, this will be 5 millisecond only, right. Okay. So now if we will see the leading SM signal SM is leading SP, then also we have a positive coincidence period of 5 millisecond, right. So similarly if we will see here, if there is the phase difference is around 180 degree, that means your SM is lagging SP by 180 degree, then the coincidence period becomes 0, right, because there is no coincidence even in the positive cycle or negative cycle. So that we are doing for positive coincidence period, so therefore the positive coincidence period will be 0 millisecond here, and the phase shift is 180 degree. Now from these figures, what we can observe is that the positive coincidence period is greater than 90 degree when your phase angle difference between the two sinusoidal signals becoming less than 90 degree, that means your coincidence period is becoming greater than 5 millisecond, and when it is greater than 90 degree, right, then it will become less than 5 millisecond, right. That is what we can see here, right. When your phase angle difference between SP and SM, we can see here it is SM and SP, and this is also SM axis, this is SM, this is SM, right. So if we will see the phase angle, if we will keep the SP as the reference signal, polarizing signal, then the SM makes different angles, right, around SP up to 360 degrees. So up to 90 degree, if you will see, it will be your coincidence period will be greater than 5 millisecond. So when exactly at 90 degree, it is coincidence period is equal to 5 millisecond, right, here as mentioned here. When SM leads by SP by 90 degree, coincidence period is 5 millisecond, but below this it is greater than 5 millisecond. And similarly, if we will see SM is lagging, or SM is lagging by SP, that means this is your lagging, right. So if your SM is lagged by 90 degree, exactly by 90 degree, then coincidence period becoming 5 millisecond, and when it is within minus 90 to 0, then we will have the coincidence period greater than 5 millisecond. That means what we can observe here, when your SM is in phase with SP, your coincidence period is becoming 10 millisecond, which is greater than 5 millisecond. So what we can observe here is, this is your trip region, right, this is your trip region. So for trip region for the phase comparator, that is cosine phase comparator, right, cosine phase comparator. So when we talk about the trip region, in the trip region your coincidence period should be greater than equal to 5 millisecond, right? When it becomes less than 5 millisecond, then we say that it is restraining. Okay. So from this coincidence period, in fact we will find the circuit, design the circuit. So now if we will see the trip region, this side, left side of this vertical axis, then your coincidence period will become obviously less than 5 millisecond, right? And this is the restraining region. When your phase angle will increase, it will become greater than 90 degree, that means SM will lead SP by greater than 90 degree, then your coincidence period will become less than 5 milliseconds. Similarly, here also when your phase angle will become less than minus 90 degree, right, it will lag by 90 degree, greater than 90 degree, that means your coincidence period will less than 5 millisecond, and it is the restraining region, right. And when it is out of phase, obviously your coincidence period is 0, already we have seen this, right. Now let us see how we can implement using this coincidence period approach, how we can see the variation of coincidence period with phase shift. Using this concept we can implement on electronic circuit for cosine phase comparator. So these are the building blocks, block diagram for the static cosine type phase comparator based on the coincidence period principle. Let us see, these are the two signals, SM and SP. SP is your polarizing signal and SM is your measured signal. Now we need to find, because we are finding the coincidence period in the positive cycle, so therefore we do not require the negative cycle to be processed. So therefore let us, in the beginning let us remove the negative cycle. So in order to remove the negative cycle we need the rectifier circuit. So in order to bypass the negative half cycle, so by using the half wave rectifier we can just bypass the negative half cycle and only we have the positive cycle. So you can see here, right. So we will get at this point only positive half cycles, and then using the squaring circuit, that is a block, squaring block you say, generally it is a electronic comparator circuit, amplitude comparator circuit, and using this we can get the square wave, because we are more concerned about the square wave. So we will find the square wave exactly with equal period of the positive half cycle, right. Using this squaring block we are using this to find the square waveform from these sinusoidal waveforms, right. So we found the square waves. Now what we will do, in order to find the coincidence period, we need to pass these two waveforms through the logical AND, right. Then if we will pass it through the logical AND, we will find the coincidence period, and that coincidence period, if it is passed through the integrator circuit, then we can very easily find the waveform which will give the integrator facility, and that output will be passed through the comparator, which will compare the integrator output with a reference value. That reference value will be set, we will see how it can, we will set the reference value, and based on that we will get some pulse waveform, and that will in fact give the trip command to the circuit breaker. So okay, so let us see how we can find the V reference, that is reference voltage to the comparator, and how after comparing this integrator output with the V reference, what kind of output we are getting, right. Let us see this. So let us see the waveforms of this phase comparator based on the comparison of the coincidence period. So first we gave these inputs SP and SM, right, these two signals, and these two signals pass through the rectifier circuit. After passing through the rectifier circuit, as we have seen, we got the positive half cycles, it is a negative half cycle is clipped, and then it is passed through the squaring block, and where we got this waveform. These waveforms we got after passing through the squaring blocks. So, two waveforms for SP and SM we got, that is SP block, we call it SP block and SM block. Now, these two blocks pass through the AND logic. Okay. So, after passing through this we will get the coincidence period. Obviously, here because they are in phase, so your coincidence period will be 10 millisecond, right. So, after finding out the coincidence period, it is passed through the integrator circuit. So, we know integrator circuit, after passing through the integrator circuit we will get the waveform like this, right. This is the output of the integrator circuit, right. And if we will compare the V reference value with this, then we will get, suppose here we are getting 90 degree, suppose the phase difference is 90 degree, then obviously it is at the threshold, and if it is less than greater than 90 degree, obviously your overlapping will be less than 5 millisecond, and under that condition your integrator output should be less than V reference, right, and therefore your comparator output should become 0, but here it is becoming a false, because here we can see the integrator circuit is becoming greater than the V reference for 5 millisecond, right. Okay. So, how it will become less when your phase difference is greater than 90 degree? When phase difference is greater than 90 degree, your coincidence period is less than 5 millisecond. So, therefore, if we will see here, this is your threshold, right. Sorry. So, this is your in fact threshold, your threshold if we will plot, this is your threshold point, right. So, when your phase angle difference between the SP and SM is 90 degree, that is the threshold, that means it is at the verge, the comparator output is at the verge of 0, right. So, then how will set the V reference? So, your V reference will be set, V reference will be equal to magnitude of COIP, that is magnitude of this waveform, this coincidence period waveform, right, into 5. So, that will give us V reference. If we will put this V reference like this, then obviously when your coincidence period becoming less than 5 millisecond, at that time when the phase difference is greater than 90 degree, at that instance your comparator output will become 0, right. We can observe this, then just do it as a homework or as part of your, you can do it and you can observe it. So, now your because when your comparator output is have some positive value or some pulses, and we can get the monostable output by passing it through the triggering circuit, right. It is very easy to implement. So, now we can see here the integrated circuit comparator based circuit for cosine type phase comparator based on the coincidence principle. So, this is the real physical circuit. By using this physical circuit we can get the cosine phase comparator. So, what are the components used here? In fact, we can see here, so these are the signals SM and SP, and now we have a half wave rectifier here, and the output of which is Vp, right. So, these are the two pulses Vp and Vm. Sorry, this is your Vm, this should be Vm, and this is your Vp, right. So, now if we will see, now if I will use another comparator, and to which I am feeding this two positive half cycle pulses, right, only positive half cycle is there for Vm and Vp. Now, if it is fed to the comparator circuit with your negative terminal 0, right, your Vn is 0 now, right, here it is Vn is 0. So, then obviously we will have a square wave at 0 crossing, right. So, that output we will get at this point, right. So, we will get two square waves at in these 2 points, right, and this, in fact, this interconnection between these 2 points will give us weird AND, right. and if we'll connect and connect one resistor and your capacitor, then it will become an integrator circuit with op-amp, right. So with op-amp, if we'll connect the resistor and capacitor, it will become an integrator circuit, and whatever output we'll get from the integrator, right, that is fed to another comparator, right. These comparators are LM339, right, and your diodes are taken as 1N4007. Already you know these components. So if we'll put this AND gate after integrator to a op-amp circuit, where your V reference is set as your, we have mentioned this is your magnitude of COIP, right, waveform into 5, right. So this is your V reference. V reference is set by varying this resistor potentiometer. Then after it is fed through, we will see that when your phase difference is greater than 90 degree, this will be sorted, right, this terminal will be sorted, and when your phase difference is less than 90 degree, when your coincidence period is greater than 5 millisecond, at that moment we will get this terminal will be floated and we will get the output voltage VCC, right. So that in fact gives us a pulse, right, and when it is fed through because this pulse will get at every positive cycle. So if again it is fed through the monostable retriggerable monostable circuit, then we will get the output, right. So finally we will get the trip signal through this. Okay, so this is your transistor through which your monostable output is passed through the trip circuit. So this is how this circuit works. This is your cosine implementation of cosine phase comparator, right, cosine phase comparator. Now after implementation, you can use this as a single block, as a static component, small component, as a cosine phase comparator, and it can be used for implementing different types of relays. Okay, so next we will see the electronic circuit for implementing a sine type phase comparator, how we can implement a sine type phase comparator. For sine type phase comparator, let us assume because we know in the sine type phase comparator the trip law is 0 degree less than equal to argument Sm by Sp less than equal to 180 degree, right. That means when your Sp or Sm is leading Sp up to 180 degree, from 0 degree to 180 degree, that means at that moment only your sine comparator will give a trip command, trip signal, right. If it is lagging, your Sm is lagging Sp, then under that condition, whatever angle may be, then under that condition it should not give any trip signal. That means under this condition we can see Sm is lagging Sp. Under this condition your trip output should be 0. So how we will get this? In fact, if we can somehow develop some spike here at Sp block, at the one edge of the Sp block, okay, the starting edge of the Sp block, then obviously when your Sm will lag, obviously there is no overlapping between Sp block and Sm block, right. That means Sp spike block and Sm block. So therefore if there is no overlapping, then obviously the trip output will be 0, right. So if there is some overlapping between Sp spike block and the Sm block, then it will give a pulse, right. So therefore whenever the Sm is leading Sp block, that means it is overlapping with the Sp spike. So Sp spike is being overlapped only when your Sm is leading Sp, right, Sp signal. So in that way it will give a signal. Okay. So that means only it will lead up to 180 degrees. So therefore when the leading is there from 0 to 180 degree, the SM block is making an overlapping with this SP spike, and so therefore there will be some trip output. So this is the basic principle by which we can implement this sine comparator. So now this is a leading condition, we can see here under this condition you can see here SP signal, we can see here SP signal, here is your SM signal which is leading SP by some angle, and here is your SP spike. Somehow we can create SP spike here at the edge of the SP block. So that when this SP spike is overlapping, here you can see SP spike is overlapping SM block, right here it is overlapping, right. So under that condition your output also, it will create an output as a spike, right, and when it will pass through the monostable circuit, it will give a signal, trip signal to the circuit breaker. So this is how it works, and how we can implement this. Let us see how we can implement. This is a block diagram how we can implement the sine comparator. So here is your SP signal and SM signal. So SP signal, both signals pass through the negative to bypass the negative half cycle. So these are the circuit by which we can clip the negative half cycle of these two signals, SP and SM. And then we have the blocks which can convert these positive half cycles of SP and SM into the square waves, right. It is already we have seen using the comparator circuit we can achieve this, and at zero crossing and detection it can convert the positive half cycle signals into the square waves, right. So then after that we need to create the spike. So therefore we must have a spike block here for the case of SP only, not for the SM. So it will create the spike, okay, and that spike also we need to bypass the negative spikes, only we need the positive spikes, okay. Whenever there is at the edge of the positive half cycle we need the spike. So this is only the positive spikes, right. Then now here the output of the SM block is fed through the inverter circuit, and it will just reverse, and it will fade as a control input to the CMOS switch. So here there is a CMOS switch, and this plays in fact an important role, because whenever there is a lagging situation, right, suppose we have your lagging, suppose your lagging condition is there, under that condition it should not give the trip signal. That means your spike should be earthed, right, it should pass through the CMOS switch to the earth, right. So how it is possible? Because it is lagging condition, under that condition your control input, it is the inversion of the SM block, right. So under that condition your SM block is 0, so your control input also becomes 0. So therefore your CMOS switch remains open. Sorry, it is your block becomes because it is negative, so it will become positive, right. So because it is 0, so your SM block output is 0. Now it will become invert, means it will become 1, right. So it will give a positive signal to the CMOS switch. Now as soon as it will become 1, and this switch will become closed under that condition, and your spike will be earthed through the CMOS switch. And under the condition when your signal is leading, SM signal is leading SP in whatever angle, under this condition, right, if it is leading SP, then under that condition what happens, it is 1, right, because we will get a block during the spike is being produced, at that moment exactly it is 1, and this will become 0. So the output of the inverter will become 0, and therefore your CMOS switch will remain open, and your spike will pass through the retriggerable monostable circuit, where it will produce a trip signal, right. This is your basic building block of the sine comparator circuit, right, and from this we can understand how it produces a trip signal when the phase difference between the SP and SM is 0 to 180 degree leading, right. Okay, so this is how it functions. So this is all about your how we can implement the phase comparators using the electronic circuits. Now we will see how we can synthesize a quadrilateral distance relay. In fact, quadrilateral distance relay plays very important role. You can see here the characteristic of quadrilateral relay, because the quadrilateral relay, this kind of relay in fact much more better, because it covers very less area in Rx plane, right. Therefore, whenever there is a situation of power swing or little small signal disturbance, under that condition your impedance does not come inside the trip region. So therefore, this quadrilateral distance relay plays very important aspect, right. Instead of putting the circular Moore relay or the impedance relay, because they cover much more area, which in fact not at all suitable when the power swing situation happens. So this type of quadrilateral relay, distance relay, in fact composed of various characteristics. We can see here, if you will see the upper portion here, it is a kind of reactance relay, right, the characteristic of reactance relay, because it is parallel to the R axis, right. And similarly, if you will see this characteristic, this is a Moore relay characteristic with some MTA angle, right, and this is also a Moore relay characteristic, and this one in fact the angle impedance characteristic relay or angle impedance relay characteristic, right. So this is exactly like equal to the reactance relay, but with some angle. So that is the angle impedance. That means in case of reactance relay we are considering the reactance, but here we will consider the impedance, therefore it makes an angle. So therefore this will be the trip region for this reactance relay, and this will be your restraining region. So therefore we call it angle impedance relay. Okay. So now let us see this, how in fact this all works, right. So we can see here this is composed of 4 types of relay characteristic, right. You can see the intersection of 4 types of relays, right. Here we can see this is your line impedance phasor, and you will see we have 4 characteristic 1, characteristic 2, characteristic 3 and characteristic 4. So now if you will see characteristic 1, in fact it represents the reactance relay with setting xn1, and characteristic 2 represents the angle impedance relay, as I told, with a setting of zn2, right, and characteristic 3 in fact represents the directional relay with MTA of minus theta 1. This is characteristic 3, and characteristic 4 represents the directional relay with MTA of 0 degree. So it is not Moore relay, as I told, this is the Moore relay characteristic and 4 in the last slide, but exactly it is not the Moore relay, because Moore relay does not cover exactly the trip region beyond this. So therefore it is the directional relay, right. So characteristic 3 is the directional relay and characteristic 4 is the directional relay with MTA. Characteristic 3 has MTA of minus theta 1 and characteristic 4 has MTA of theta 2. Okay. So that means your in case of characteristic 3 your voltage is leading, then the maximum torque position, and in characteristic 4 your voltage is lagging if we will compare with the maximum torque position, right. Okay. So, these are the characteristic. As I explained previously, it is the Moore relay, it is in fact not the Moore relay, it is the directional relay characteristic. Okay. So, just rectify it. This is the these characteristic 3 and 4 are the directional relay, not the Moore relay. Okay. So, now I can see what are the quantities we will feed into as measuring and polarizing quantities. So, for reactance relay already we know that to a phase comparator we feed Ix1 minus V. V is in fact the voltage seen by the relay, right, and I also the current seen by the relay. Similarly, the polarizing quantity will be Ix1, and this is the signal Sm and this is Sp, right, as we feed to the phase comparator. Similarly, your to the for angle impedance characteristic, our measured quantity will be Izn2 minus V, and your polarizing quantity will be Izn2. Similarly, for the directional relay with MTA minus theta 1, our measured quantity is I and polarizing quantity is V, and for directional relay with MTA theta 2, your measured quantity will be I and your polarizing quantity will be V. So, now these are the measured and polarizing quantities. Now, we will see how we can implement, right. So, let us consider first these two characteristics, characteristic 1 and characteristic 2. They are in fact representing the reactance relay. How we know when we implement the reactance relay with a cosine type of phase comparator, your measured quantity will be Ix1 minus V, and your polarizing quantity is Ix1 Ixn1, and then we will get the trip output, right. So, this is how we can implement the reactance relay, that is characteristic 1, right. Now, how we can implement characteristic 2? So, this is also by using the cosine type phase comparator, in which again we feed Izn2 minus V as the measured quantity and Izn2 as the polarizing quantity, right. So, this is how we can implement these two characteristic. Now, the third and fourth characteristic, how we can implement. This is your characteristic 1, this is characteristic 2, this is characteristic 3 and characteristic 4. So, characteristic 1 and 2 we implemented, then we will see how we can implement 3 and 4 using the phase comparators. So, because this is a directional, this is a directional relay, right. So, therefore, it is very easy to implement just by putting V and I across the cosine type phase comparator, we can just get the trip output, right. So, theta 1 is your MTA angle which is lagging to V. This is in fact your V is lying as reference here, right, this is your V. So, therefore, the angle difference between the V and this is minus theta 1, right. So, therefore, your MTA is minus theta 1, okay, and this can be implemented using this by giving V and I to the cosine type of phase comparator. Similarly, here also we can implement characteristic 4. This is also a kind of directional overcurrent relay which is implemented, and here MTA is theta 2, right. We can see here MTA is making an angle of theta 2 leading to the voltage phasor, right, as voltage, because voltage is the reference, right. So, now characteristic 4 can be implemented just by putting V and I to the cosine type of phase comparator. So, all the 4 characteristic we have implemented. Now, if we will, how we will find the intersection of these 4 characteristic, if we will make it a pass that all the trip output of these comparators through an AND gate, then we can very easily find this quadrilateral relay, right, the characteristic of quadrilateral relay. This is your characteristic of quadrilateral relay, right. Okay. So, just by ANDing these outputs of the comparators we can find. Now, we will find this is characteristic 1 which is reactance relay, this is characteristic 2 which is angle impedance relay, characteristic 3 is your directional overcurrent relay with MTA minus theta 1, and characteristic 4 is your directional overcurrent relay with MTA equal to theta 2. Now, all the trip outputs of these 4 comparators are passed through the AND gate, and the final trip output will give us the characteristic of this special type of quadrilateral relay, right. So, therefore, in this way we can implement we can design various types of quadrilateral relay using these static comparators, right, static comparators. Just using various types of combination we can get various type of characteristic. So, this is how in fact the static comparators play a very important role in designing the relays. So, now we will in fact stop here. Okay. So, we covered the static relays and finished it, completed, and next class onwards we will see the numerical protection system, or we call it digital protection system. So, we will continue with that, and then this is your one portion, and another portion will cover your circuit breaker after this digital protection scheme is finished. In fact, we cannot cover this digital protection scheme completely because it is a very huge volume. So, we will cover very few aspects, introductory aspect, then few of the digital schemes, right, not whole of the digital protection scheme. So, thank you very much. Thanks a lot for your kind attention.